Okay, so we're going to look at empirical method of probabilities. So empirical method is really when we have no clue what's going on. So like when we roll a die, we know all the things that could happen when you roll a die. It could land on a 1, 2, 3, 4, 5, or 6. We know the probabilities of all those events have the same likelihood of occurring. So empirical probabilities are more to deal with events that we don't, that are things we have to experiment to know about. So we can do experimental probabilities on things like a dice roll. Doesn't mean we necessarily have to do it. So empirical is really used when we're trying to, we're looking at samples and we're making guesses from them. So the law of large numbers says that if we repeat a probability experiment a large number of times, then the proportion of times that a particular outcome occurs is likely to be close to the true probability of the outcome. So the empirical method consists of repeating an experiment a large number of times. So it's applying that law of large numbers, ideally. Doesn't mean it always does. And using the proportion of times an outcome occurs to approximate the probability of the outcome. So the more times I repeat this experiment, this empirical method or empirical probability should be closer and closer and closer to the true probability. But all it is going to be the frequency of the event and the total number of occurrences. So actually those last couple problems that we were doing, this was actually using an empirical method because I actually don't know how many people in a certain age group are using that app unless I go out and I do a study. This required me to do a study, do an experiment to gather this information. So another example, in recent years, there were 313,752 births in the US to low birth weight babies. So that means they weigh under 2,500 grams, which I forgot to figure that out in pounds. While 3,477,960 babies had a birth weight of 250 grams, 2,500 grams or more. We will approximate the probability that a newborn baby has a low birth weight. First thing we need is we need the total number of babies. I have babies that weigh less than 25,000 grams, or sorry, weigh less than 2,500 grams, and then I have babies that weigh more than 2,500 grams. So what I need to do is I need to figure out my total number of babies. So all I'd have to do is just add those together. So that should cover all my babies because I have low birth weight babies, and then I have babies that are not low birth weight. If I add those together, I should end up with 3,791,712 babies or births. So if I want to figure out the probability of a low birth weight, I had to do an experiment. I had to go out. I had to go collect a bunch of data on babies. So this is the total number of babies there were. We had 313,752 of those babies were low birth weight. So that is going to be approximately about 8% of my babies have a low birth weight. Okay. That's all empirical method is. It's nothing new for the most part. It's just in this case, we actually have to gather data where the other kind of probability, we didn't necessarily have to gather data. It was that we could look at a situation, we can estimate what should be going on. So there are 100,000 voters in a city. A pollster takes a simple random sample of 1,000 of them and finds that 513 support a bond issue for the public library, while 487 oppose it. We want to estimate the probability that a randomly chosen voter supports the bond issue. We figure out probability of supporting the bond. In this case, we already know that we know that there is 100,000 voters, but the pollster only looked at 1,000 of them. And of the 1,000 of them, we see that only 513 support the bond. So the probability that somebody would support the bond, just we randomly chose a voter, is 0.513, or we could say 51.3%. Remember, when we do probabilities, we do tend to talk about them as decimals in statistics and studies and stuff like that. We know in the real world, we tend to talk about it in percent. But for the most part, you should be really like recording your answers as decimal more than anything else. Okay, here's another one. So a company is conducting a survey of randomly selected US adults to determine how they read books during the past year, if at all. The pie chart shows the results. Note that digital books include ebooks. Okay, don't worry about that because that's not part of our problem here. What's the probability that a randomly selected person will have read only printed books? Well, we see here 560 have read printed books, but out of how many? So in this case, we need to figure out that total number of people in study. So we see we have 409 people read no books. We have 425 people read both print and digital books. We had 108 read only digital books. And we had 560 read printed books alone. I almost feel like these numbers are off because I don't think that many people actually read. It goes wrong. Altogether, okay, so I thought it was, we get 1,502 people were in this study. So the probability that they read print only would be 560 out of 1,502. Which is going to be roughly, this is definitely going to have to be an estimated answer, 0.337. So about 33.7% of the people that were surveyed said that they read print-only books. So approximate probabilities by using a simulation. This is going to have to require our calculator here in a minute. So in practice, it can be difficult or impossible to repeat an experiment many times in order to approximate a probability of the empirical method. So something, like we know that is something we know that is random and has the same probability of happening for each event is something that we can simulate here. So in some cases, we can use technology to repeat an equivalent experiment many times. Conducting a virtual experiment in this way is called a simulation. So we are going to use our TI-84 and we're going to do a random simulation. What we want to do is simulate the roll of a 8-sided die, and we want to roll it 50 times. And from there, we want to calculate the empirical probability and the theoretical probability of computing a 5. So let's first look at the calculator before we come back to this question. Okay, so let's say we wanted to demonstrate rolling a 6-sided die. And we want to simulate this for, let's say, 100 rolls. What we would do is we go right here where it says math, and then we move over to where it says prob, because that's our probabilities. And then we go all the way down to number 5. So this is supposed to be a random number. So we enter that. So what we need, if we talk about a 6-sided die, the lowest possible number I can get is a 1. So this is random integers, by the way. And the largest number I can get in a rolling a 6-sided die is a 6. So I put low 1, upper 6. N is going to be the number of times I'm going to conduct this experiment. This is going to randomly give me integers between 1 and 6. So as we see, it's going to give me my whole list of numbers here. All right, so depending on what you're using, you could store this someplace. See, you actually put it in there. Nope, it didn't. So the TI-84, most of them, what you actually can do is you would put this part in and then you'd put store and you could put it into the list. Okay, sorry. It was throwing me off. It wasn't working like my normal TI-84. So yeah, in this case, there you go. If I go store, sorry. If I go second, and then this little part down here, so that little negative, that puts answer. I have my answer. Then I hit the store button. I can put it, if I want it in list 1, go second, L, and it puts it all in list 1. Oops. Okay. There we go. We see it's giving us all these different numbers randomly between there. Then we can run some stuff on it, like just out of curiosity, run your run var stats if you wanted to. So it gives you a way to like generate some data and then you can kind of look at it. We're not going to use the one var stats, just showing you can use other stuff for it. Okay. But like I said, that stimulates. Oops. Somewhat funky there when I was trying to click on that. But it just simulates those die rolls. Okay. So I'm going to clear this because we're going to do something different here. So if you go back to our problem, we wanted to look at an 8-sided die. So an 8-sided die would roll 1, 2, 3, 4, 5, 6, 7, or an 8, and we want to do it 50 times. And we want to calculate the theoretical and the empirical probability that we roll a 5. Okay, so let's go back here. So theoretically, if I have an 8-sided die and I want the probability of rolling a 5, I have 8 choices for my die, 1, 2, 3, 4, 5, 6, 7, 8, and only one of them is a 5. So the probability that I would roll a die and get a 5, I've had an 8-sided die, is theoretically going to be 12.5% or 0.125. Empirically, if I do actually have to do and study, we said that we are going to roll a die 50 times. What we want to see is how many of those 50 times am I actually getting a 5. So we go back to math, go back to probability, and go back to number 5 there. So a random integer. Our lowest possible roll on an 8-sided die is a 1, and now our largest is an 8. And we don't want to repeat this 100 times, we want to repeat this 50 times. There is my whole list of numbers here. Because I want to see them, I'm going to go to second, and I'm going to put in that answer. I'm going to go to store, and I'm going to put them in my first list. So second, 1 to get an L1. So we want all the time I get a 5. So let's see. We have a 5. There we go. We got 1 here. 2. This one's going to be weird. 3, 4, 4 times. So if we calculate 4 out of 50, that's actually going to give me 0.08%. So one of the interesting parts about empirical probabilities is that even though we know in the long run what should happen is it's a 12.5% chance I would roll a 5, according to this experiment, it's an 8% chance that I would roll a 5. And this is generally the issue that we have with empirical probabilities, which is mostly what we use in statistics, is that, this was completely 100% randomly generating numbers. And I randomly get a probability of 8%. So, like I said, this means that, anytime that we do collect samples, there's a chance that we randomly collect a sample that's not very representative. This that we collected must not be very representative because my probabilities are not the same. I don't have the same proportion of 5s that I should have. So this is one of those things that you always have to worry about, is that there's theoretically what should happen. The population would be your true probabilities. And when we do samples, those are like those empirical probabilities. And the larger and larger our samples are, the better our estimates should get. If I did this for 100 rolls, ideally, I would get a much closer number. I'm not going to experiment with that because usually when I do that, I get it wrong, but especially in videos. But like I said, larger and larger samples should be a little better about this. Because theoretical probabilities, this is assuming that I did an infinite amount of rolls. If I do it an infinite amount of times, I should get 1 out of 8 are going to be a 5. Or like I said, 12.5%. But like I said, we're doing an experiment. We only have a finite number of rolls that we're looking at. We could get any kind of probability. And in this case, we get an 8%. So it's just one of those things to be aware of, that when you're doing anything with statistics, you might do the best you can. We did it as randomly as we could, and we still didn't get a representative sample.